So the topic of today's discussion is deadlock. Deadlock, it is something that which is observed by the operating system, a phenomena that which is taking place in the system. Operating system, it identifies it, and deadlock is something that which the operating system or the system, it does not want to have. So what deadlock is, we will be coming on to that point. But before that, we have to think of a multi-programming environment where we are having various processes, and these processes which are existing at the same time and are thinking of having execution at the same time. That means we are thinking of having multiple processes and having their execution at the same period of time. By having, if you are having multiple processes, then in that case multiprocessing is something that which can take place. But if you are having a single process in a single processor, then also in an interleaved way you can think of multiple processes existing at the same time, and sharing is something that which takes place. So processor time is something that which is shared between the processes. Memory is something that which is shared between the various processes, and various processes, they are dining at the same time. Multi-programming, it speaks of a phenomena where multiple processes, they are existing at the same time. What a process is, the basic concept: process, it is a program in execution. Multi-programming, it speaks of a phenomena where you are having multiple programs housed onto the memory at the same time. So when I speak of memory, resource. When I speak of CPU, resource, being shared by various processes. Memory, processor are not only the resources that which the computer system, it gives to the processes. There are various other resources also, and during the process lifetime, the various processes which are existing at the same time, they are competing for holding the resource. Once they are able to hold the resource, then only whatever task they are thinking of, it is going to get accomplished. So you can think of a competitive environment where several processes, they are competing for resources. In a multi-programming environment, that is the scenario. So when you are thinking of such a scenario, you can always think of a situation where if suppose a process is there, the name of the process is P1, and you are having another process, the name of the process is P2. P1 is holding, we are thinking of a particular point of time where P1, it is holding a resource, say R. And likewise, P2, it is holding a resource R2. Now, at this point of time where this is the state, that is P1 holding a resource R1 and P2 holding a resource R2. At this point of time, say for further execution, P1, it requires another resource, that is R2. P1, it cannot go further until and unless it is holding R2 also, because for the next execution it requires R2. And likewise, P2, it requires R1 for further execution. So we'll be seeing a scene like this: P2 requiring R1 and P1 requiring R2. And say in the system you are having only one units of resource type R1 and R2. Then you will observe a phenomena that is called deadlock, which says that these two processes cannot go further because what they are demanding for is currently occupied by another process, that which is waiting for a resource to come out from the next one. Got the point? So P1 is waiting for a resource holded by P2, and likewise P2 is waiting for a resource holded by P1. both the processes, they will not change their state, because what they are wanting is something which is going to come out of another waiting process, which is waiting for a resource to get out of the first one. And this is neither agreeing to deallocate the resource, and this is also not agreeing to deallocate the resource. So both the processes, they are deadlocked. This is what deadlock is. Deadlock, it speaks of a phenomena where you are having a set of processes. These set of processes, they are holding a set of resources, and at the same time they are waiting for a set of resources which could come out only out of a waiting process in the same set. So in today's presentation we'll cover all these points. Introduction to deadlock is something which I already gave a brief introduction to deadlock, where this is the phenomena. Two processes are there, they are not changing their state because they are waiting for something that which is ordered by another process. Then comes system model. So as I already told you that processes are there, and during the process lifetime, whatever the objective of the process is, to accomplish the to accomplish the objective, each and every process will require a set of resources. They will be having the resources by demanding it to the operating system. The demand it goes, the operating system, it checks. There is a table that which operating system maintains, that is called resource table, where it checks the availability of the resource, and then it gives away the resource to the process. The process, it makes a utilization of the resource, and then once a process it is able to make a utilization of the resource, it must make a deallocation of that. So operating system, it specifies a model through which a process, it makes a request for a resource. The operating system, it checks it, and then looking to what the current status of the resources is from the resource table, the operating system, it can make an allocation of a resource to a process. The process, it is going to make a utilization of the resource, and once it is able to make a utilization of it, it is going to make a release of it. Beside that, there is one thing that should happen. While a process, it is making a request for a set of resource, there should be a condition that the amount of resources that which are demanded by a process, it must not exceed the value that which is obtained by the system. For instance, a process, it cannot ask for 2 CPUs if the system is only having one. You cannot go beyond the limit that which the system it is having. If the system it is having 2, you cannot ask for 3. That is the thing. Operating system, it also specifies a way through which this process, it can have the resource, and that is system calls. So there are a set of system calls which the process, they will invoke in their structure. Operating system calls, the execution, it goes via the operating system. So system call invocation is something that which is required to have an occupancy of a resource. Requesting is going to be via the system call. Operating system is going to make an assessment, and then resource allocation will take place. After resource allocation, utilization, and then release via system calls. Now in this case, there are 2 resource types. 2 resource types having different nature. Say R1 is CPU, and say R2 is suppose printer. So we are thinking of 2 different resources. But deadlock, it may happen with the same resource. 2 processes, they may get deadlocked on the same resource also. You can think of a system which is having 2 printers and two processes are there, and both these processes, they are requiring two instances of printer, and both these processes, they are holding one instance. So in that case also a deadlock it may happen. You are having two instances of the same resource type, you are having one, and none of the processes, they are ready to release what they are having, so that the other one, it can do its task and then make a release, and the work of the second one, it could get accomplished. This is not what is happening. The thing that which is happening is, you are having two instances, these two instances distributed one each to each of the processes, and both these processes, they are not changing their state. So deadlock, it may happen with the same resource is there, and deadlock it may happen, and the second scene is already there with you. Then the third topic is necessary conditions for deadlock. So there are four necessary conditions for deadlock. If these four conditions, they are simultaneously holding, then you can say that deadlock, it may happen in the system. So the first is mutual exclusion. The second is hold and wait. The third is no preemption. And the fourth is circular wait. Mutual exclusion is something that which this term already appeared. You might have heard it many a times. In the study of operating system, you hear this term when you are reading, when you are making an exploration of synchronization, and you are thinking of a resource that which is shared by a number of processes. You are thinking of a cooperative environment, and there are various resources where the utilization, it could go only in this way. So mutual exclusion, it speaks of non-shareable resources. When you see a computer system, you will see various resources, the nature of which is non-shareable. The execution, it could not go in a shared way, because the very nature of the resource, it does not allow them to go in that way. Like the printers, for example, printers non-shareable in nature. So there are various resources which are non-shareable in nature. The system, they have to take care of them, and mutual exclusion is the way through which the processes, they can make a utilization of them. So in the system, this is something that which is observed because of the nature that which is associated with the resource, that is non-shareable nature. The second is hold and wait. The name itself, it is telling that holding something and waiting for something. So you have to think of a scenario where there are a set of processes which are existing, and the thing that which you will observe with these processes is, they are holding a set of resource, at least one, and they are waiting for a resource that which is holded by a waiting process. So hold and wait, it speaks of that. Then comes no preemption. No preemption is something that which again, many a times you might have heard this word. No preemption, it speaks of the very nature, the nature that which you are holding a resource, and you will deallocate that resource voluntarily. For instance, a process is there and it is holding a resource. It is going to deallocate that resource only when its work on that resource, it is accomplished. So that is what no preemption is. This is also something that which you may observe in systems with various resources, the very nature it speaks of this. And operating system designers, they always try to go in the other direction to have the maximum resource utilization. If you are going by this way, there are various problems, but there are various resources where this is something which is very important, and there are various events where this is something which is important. However, utilization of this, if you are making a utilization in the system, then in that case you may suffer from something that is called deadlock. Then comes circular weight. Circular weight, when you see these four conditions, you will say that you will find a relationship between these conditions. Circular weight, it speaks of a phenomena where, again, if I consider this case only, then I am having two processes, and this process, it is waiting for something that which is holded by this, and this is waiting for something that which is holded by this. So I may see a chain, I may see a cycle. This is what is circular weight. So you can think of n processes starting from P1 to Pn. P1 is waiting for something holded by P2, P2 is waiting for something holded by P3, Pn minus 1 is waiting for something holded by Pn, Pn is waiting for something that which is holded by P1. Pn is the thing is Pn is waiting for something holded by P1. So I am having a cycle, I am having a chain, and if this chain is there, then that is what is circular weight. Then the next topic is resource allocation graph. Resource allocation graph is a directed graph structure we can use it to characterize deadlock, to represent deadlock. If a deadlock it is there in the system, by means of this resource allocation graph we can actually observe, okay, this is the state, and this state, it specifies that deadlock it may happen in the system. So to have a better idea of resource allocation graph, which is a directed graph, since it is a directed graph, you will be thinking of vertices and you will be thinking of edges. And directed graph means directions will also be there. Vertices I will be classifying into two types. Set of processes will be there, and set of resource types will be there. What I said, we may classify the vertices into two types, set of processes and set of resource types. So PPP specifying processes, R specifying resource types. Now there is one thing that which you know, that is you may have multiple instances of a resource type. Like in a system you can have two CPUs, in a system you can have two printers, in a system you can have two CD drives. So this resource allocation graph is supposed to cover that also. So how it covers? By means of dots. If two instances are there, two dots will be there. If one instance is there, one dot. If three instances are there, three dots will be there. Now this is a graph which will comprise of vertices, which we already classified into these two categories, that is set of processes and set of resource types. Likewise, edges are also there, and edges are classified again into two types. The first is called the request edge, and the request edge will go from here to here. That is a request edge. It is an edge which goes from a process to a resource type, and we are having assignment edge which goes from the resource type to the process. So we are having two types of edges. This is called a request edge, which goes from process to a resource type, and we are having assignment edge which goes from the resource type to a process. This may request for this. There is something that which is holded by this. So this is a request edge, this is an assignment edge. Assignment edge. Assignment edge. So this is a resource allocation graph. This resource allocation graph, it speaks of, now there are certain interpretations in forensics that which you can make out of this. You can actually identify sets of processes, sets of resource types, and set of edges. You can actually identify these three sets out of this resource allocation graph. You can actually tell about the instances, the number of instances of each and every resource type. So you are having 3 instances of resource type R1, you are having 2 instances of resource type R2, you are having 1 instance of resource type R3, 3 instances of resource type R1, 2 instances of resource type R2, 1 instance of resource type R3. You can actually speak about the state of the processes also. P1 holding resource type R2, waiting for resource type R1. P2 holding resource type 1 instance of resource type R1, 1 instance of resource type R2, 1 instance of resource type R3. P3 holding 2 instances of resource type R1, waiting for 1 instance of resource type R3. So all these things we may actually observe out of the resource allocation graph. This graph, there is one thing that is called cycle. If a cycle it is there in the resource allocation graph, then we may say that a deadlock it had happened in the system. In case multiple instances of resource type it is present, then in that case, even if a cycle it is present, you cannot say that a deadlock it had happened in the system. Although I already specified at the starting point itself the structure through which I specified what a deadlock is. single instance of resource type. So that was also a resource allocation graph. You can think of that structure as a resource allocation graph only, where single instances of resource type it was present. A cycle that was present, that was actually specifying deadlock. So if single instances of resource type is there, resource allocation graph, it specifies a cycle in the resource allocation graph. You are actually able to observe a cycle in a resource allocation graph having single instances of resource type. You can say the deadlock it had happened in the system. That is something that which is necessary as well as sufficient. But if multiple instances of resource type is there, you cannot say, because there are situations where a cycle it is there in the resource allocation graph, but still deadlock it is not there. We'll speak on that later on, and another video will speak of that. Then comes methods to handle deadlock. So methods to handle deadlock, there are three ways through which we can make a handling of the deadlock. The first way is three ways are there. The first way, it says that you will not allow deadlock to happen in the system, and there are two ways of ensuring that. The first way is called deadlock prevention, and the second way is deadlock avoidance. The thing is, we are thinking of a case, we are ensuring that deadlock it is not going to happen in the system by means of two ways. The two ways are called deadlock prevention and deadlock avoidance. The second way is called deadlock detection and recovery, where we are allowing deadlock to happen in the system, and then we will be making a detection of deadlock, and then by means of certain algorithms we'll be detecting whether deadlock it had happened in the system or not. And then in the second stage we'll be invoking certain strategies by which we'll be making a recovery from the deadlock which had happened in the system. The third way is the way where it says that we'll be dealing with it in a completely altogether different way, where we are thinking that deadlock is something that which rarely happens in the system. So if you are having a separate strategy that is going to make a detection, or you are having a separate mechanism which is going to deal with it, and if it rarely happens, then in that case you are actually missing out it, because deadlock handling and having a separate mechanism for that, it is going to incur some cost, and you don't want that cost to come into picture. So beside of having a separate mechanism, we'll be handling it manually. We'll be restarting the system. If it happens, we'll be restarting the system, because if deadlock it happens, then in that case the number of processes that which are going to get deadlocked, because deadlocked processes, they will be holding a set of resources.